DuckDB under the hood, Module 8. Sometimes an index makes a query faster. For example, 4 milliseconds with an index versus 109 milliseconds without. But sometimes it's the other way around. Here's a query on the OLAP column, finding 1,518 matching rows out of 150 million. With an RT index, the query takes 0.004 seconds. Without the index, it's 109 milliseconds, or 27 times slower. But if you add 40,000 duplicates per key, the index makes it slower. DuckDB under the hood. This is Module 8. DuckDB's ART index stands for Adaptive Radix Tree. It is an in-memory index structure designed for fast equality lookups and point queries. DuckDB uses ART to enforce primary key, foreign key, and unique constraints. Every constraint in DuckDB is backed by an RT index automatically. Unlike a B tree, RT adapts its node size to the actual key density. Sparse key ranges use smaller nodes, dense ranges use larger ones. This keeps the tree compact and cache-friendly. The result is faster key lookup on modern CPUs compared to a traditional B tree index. DuckDB only uses an RT index when it expects few matching rows. The threshold is the maximum of index scan max count and index scan percentage times row count. The defaults: max count of 2048, percentage of 0.001, up to 0.1% of rows. For 15 million orders, the threshold works out to approximately 15,000 rows. Set both to 0 to disable the index entirely, useful when benchmarking to compare full scan against index scan. Let's consider index maintenance and what update costs. Creating an index is itself expensive as it walks all rows and builds the trie. Every insert or update on an index column requires ART maintenance. ART must insert or delete the affected key, which involves pointer juggling in the trie. There is no parallelism during update with index maintenance today. As a rule, drop an index before bulk updates and recreate it after. Let's look at the duplicate trap, where index scan is slower than sequential scan. An ART lookup returns a list of row IDs matching the key. With few duplicates, you get a small row ID list and a small random access pattern, which is fast. With many duplicates, you get a large row ID list and many random jumps across column chunks. Sequential scan reads chunks in order, which is CPU friendly and cache warm. DuckDB still picks index scan if the row count is below a threshold, even when it hurts. Here's what RT indexes do not help with. DuckDB does not use RT leaves for sorted traversal when using order by. For minimum and maximum aggregates, DuckDB does not walk the leftmost or rightmost leaf. Like predicates are rewritten as conjunctions internally, so there is no index scan. For conjunctive predicates, DuckDB does not intersect two index results. These are known gaps, not bugs, and the plans simply do not exist yet. We attach the TPCH scale factor 10 database and switch to it. The orders table holds 15 million rows, with OClerk as a varchar column storing clerk identifiers. We create an RT index on OClerk. This takes several seconds. DuckDB is building the Adaptive Radix Tree over all 15 million keys. With the index in place, we can now observe when DuckDB chooses to use it and when it falls back to a sequential scan. This query shows the memory usage of the Adaptive Radix Tree index. It selects the tag and memory usage in bytes from DuckDB memory. It filters for entries where the tag equals ART index. Next, this query calculates the threshold for index scans. It selects the greater value between index scan max count and a percentage of the total rows in the orders table. This threshold determines when DuckDB switches from index scans to full table scans. The explain plan for the equality predicate on OClerk shows an index scan using orders.clerk.idx. DuckDB estimates fewer than 15,000 matching rows, so the predicate falls below the threshold and the index fires. The index scan returns only the matching row IDs, then fetches those rows directly. This is 27 times faster than a sequential scan for a highly selective predicate. Setting both threshold values to 0 disables the index scan entirely. DuckDB will now fall back to a sequential scan regardless of how selective the predicate is. Now we build a table T with 100 million rows but only 2,500 unique values in column I. On average, each unique value appears 40,000 times, the high duplicate case. We then create an index on column I. This sets up the duplicate trap. The index will fire but will perform worse than a sequential scan. With 2,500 unique values across 100 million rows, a single value matches 40,000 rows. That is still below the default threshold, so DuckDB selects the index scan, but the index returns 40,000 row IDs scattered randomly across column chunks. Each random access crosses chunk boundaries, causing cache misses. The index scan ends up slower than reading the column in order. This is the duplicate trap. The index fires when it shouldn't. Now we recreate table T with 6,250,000 unique values across 100 million rows. Each unique value appears on average 16 times, far fewer duplicates than before. We create the index again on column I. With fewer duplicates, the index lookup returns a small row ID list, and the random access pattern is short enough to be genuinely fast. With 6,250,000 unique values, a single predicate match returns only 16 rows. The index scan is now genuinely faster than a sequential scan. The plan still shows an index scan, the threshold is the same, but now the index earns its cost. The key insight, the duplicate count, determines whether the index scan is a win or a trap. Here is the measured difference, an equality predicate on the indexed column. 3 milliseconds, the RT tree traversal touches a handful of nodes and returns the matching rows directly. A like predicate on the same column, 86 milliseconds. No index path is available, so DuckDB reads every row, 29 times slower. The index is only faster when selectivity is low. Above roughly 2% of the table, the sequential scan costs less per row than the pointer chasing through the tree. Here is an exercise for you. Predict whether each query will use an index scan or a sequential scan. The table is orders, which contains 15 million rows, and there is an index on OClerk and OOrderKey. The first query filters where OClerk equals a specific clerk ID. The second query uses a like predicate on OLerk. The third query filters on OClerk and OOrderKey. The fourth query orders by OOrderKey. Verify your predictions using the explain analyze command. You can find the answers in the exercise file. We reset both threshold settings to their defaults. This restores the ART scan decision logic. DuckDB will again choose between the index and a sequential scan based on how selective the predicate is. The index on OClerk is still in place from the walkthrough. With defaults restored, let us verify the 4 exercise predictions using explain. Query 1, equality predicate on OClerk. The plan shows an index scan using orders, clerk IDX. Only 1,518 of 15 million rows match, well below the threshold. The index scan is 27 times faster than a sequential scan for this predicate. Query 2, like predicate on OClerk. The plan shows a sequential scan, not an index scan. DuckDB rewrites like internally as a conjunction of range predicates. The ART index is not invoked for like patterns. Query 3, and predicate on OClerk and OOrderKey. The plan shows a sequential scan. The index on OClerk is not used here. Adding the OOrderKey condition changes the optimizer's cost estimate. DuckDB has no index on OOrderKey, but zone maps can prune row groups on that column efficiently. The optimizer chose sequential scan over index scan, applying both filters in a single pass. Query 4, order by OOrderKey. The plan shows a sequential scan followed by a sort operator. DuckDB does not traverse RT leaves for sorted output. The index on OClerk cannot help with ordering on a different column. Let's recap what we covered in this module. The RT threshold, the maximum of max count or percentage times rows, controls when the index scan fires. Selective lookups mean that an index scan can be 27 times faster than a sequential scan. Index maintenance means that a bulk update with an index can be 10 times slower. The duplicate trap means that high cardinality results make the index scan slower than a sequential scan. And finally, ART does not accelerate order by minimum and maximum aggregates or like in the current DuckDB. Next up, Module 09, Query Execution Pipelines.